Hello, everybody. I want to make a tutorial video for Lab 8. Let me make it here, yeah. So in this lab, you are gonna learn how can you connect op-amp circuits to create inverting and non-inverting and summation circuit as well. Okay. So I can tell you from my experience, this lab is not difficult, okay? However, many students, if you don't watch this video, if you don't pay attention, if you don't give it enough time before the lab, many students will struggle, not because it's difficult, but mainly because we're gonna use many things at the same time, okay? So what we're gonna use here, number one, we're gonna use two power supplies, okay? Number two, we're going to use function generator in one circuit. We're going to use one channel for function generator, and then I'm going to use another channel for function generator. Number three, we're going to use a oscilloscope. I think in one circuit you need to use two channels of the scope. That's okay. And for the other circuit, you need to use three channels. Okay, it's not difficult if you. The problem is that we have been using power supplies for many labs, right? And also function generator and oscilloscope, we use them in the last lab. So you should be able now to use them, right? So anyway, let's see. But again, if you watch this video, I will do my best to make sure this lab, again, this lab easy for you. By the way, again, this lab is not difficult. However, it is only connection. You need to connect too many things. Okay, number one. As I explained in the lecture, guys, we have op-amp. I already explained what is this, how can we use it, whatever. Okay, so number one, how it looks like. So it is, yeah, this is how the op-amp looks like. It's a chip, as I told you, it has 8 pins. This is the number you should see, 741. LM, okay, 7741. Okay. So you need to search your kit to find this one here. Okay. One more thing very important, guys. You can see a notch here, a dot here, or a notch here. Okay. What this means? It means this is not only for this chip, but this is true for any chip. Okay. Once you see notch in this side, that means I am telling you this is pin number one. This is pin number two. This is pin number three, four, and then here 5, 6, 7, 8. So you have it has to go this way, starting from the notch, from this notch here. Is that okay, guys? This is how can you find the pins. This is number one. Number two, yeah, this is how the chip looks like. All what we need, okay, here for this chip, we only need here pin number two, because this is the inverting input. This is the negative. For the positive here, this is pin number 3, and the output is pin number 6. And now you remember I told you you need to connect the bias. So when you connect the bias, the positive bias has to go to pin number 7. The negative one has to go to pin number 4. Okay, that's all what you need. So we don't need the other pins. Or we only need pin 2, pin 3, 4, 6, and 7. Okay. Number 2, which is very important, guys. How you are gonna connect it. Look, as I told you before, for the breadboard you have, okay, let me see. For the breadboard you have, all this column is just one node. So if you connect a wire here, internally they are connected actually. So if you make a wire here and wire here, okay, so actually it's a short circuit. It's already internally connected. That means, look here, this is, for example, pin number 7 is here, right? If you want to connect anything to pin number 7, I can put it here. You 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 can put it. They are the same. Okay, this is number one. Number two, so look here. We have a separation here. Meaning, which means, look here. All these holes here, just one node, short circuit. And also all these nodes are short circuit. However, they are not connected together. You see what I'm saying? That is why, for example, as you see here, guys, this is pin number 1, pin number 2, pin number 3, pin number 4, 5, 6, 7, 8. Okay. So here, because these ones here are not connected to this one, so that's why pin 1 is not connected to 8. right? So very easy. Every time you want to connect something to pin number one, just put it here, 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 here. It's the same thing. Same thing if you want to connect anything for any other one, for example, pin four, you put here anywhere here. Okay. Always for any chip, because in the future we're going to use this chip again in lab 11. But I also in one lab, another lab, we're going to use also another chip which is triple three. It's the same thing. For any chip, you have to put it here this way. Okay. Please, if you put the chip this way, it's a mistake. You know why it's a mistake? Because actually you are connecting these pins together. You see what I'm saying? So it's wrong. So always for any chip, we have to connect here because this is a separation. These parts are not internally connected. This is a separation. Okay. Uh, so one more. Okay. So let's see now. So now let me come here. Yeah. Sorry. Yeah. So now, how the first thing you have to do, I have to connect the bias voltage. As I told you in the lecture, for the bias voltage, you need to use two channels from the power supply. As you see here, this is like one channel for the power supply. I'm just saying the voltage here is VCC, whatever, any value, right? For this one here, this is second channel of the power supply, so it's also another supply, and the voltage of this power supply, VEE, right? So here, what I want to say here is that they can be the same. And actually, most likely, we'll make the same. For example, here, if you make this one 15, this also will be 15. Keep in mind, this point here has to go to ground. So if you do that this way, guys, so here, this terminal here, this part here should be equal to, okay, positive 15. And this one here should be negative 15. And this part here is the ground. Is that okay? So this is how you should. So now you need two channels from the power supply to connect them as shown here. Okay. And then positive 15 has to go to this one. Which pin is that? Let's see. Which pin is that here? Sorry. Yeah, here, this is pin number 7. Okay. So for example, if you select 15 and this is a negative 1. Okay. So yeah. So now, because our circuit now has, or the way usually we do it, guys, to avoid confusion, because this is a very important thing. I'm going to tell you something funny. When I was a student, one time I did not pay much attention to the value of the power supply. I just connected it. I found like very small explosion and crack. I actually damaged the chip. Okay. Why? Because the voltage was too high. That's why you have to be careful. Don't don't to connect the power supply until you check the voltage first. Make sure it's, because if you apply too very high voltage, you are gonna damage it. You're gonna crack. Okay. I'm going to tell you about like very professional habits usually we do. In the professional habits we do, look here, remember from what I explained to you before, all these lines vertically here connected together. Okay. So although there is a separation here, but no, that's what I'm telling you. All of them, these are connected together. And usually, same thing for this ones here, right? And usually these ones are used for the supply. For example, I can consider here, I can connect ground here. Okay, so all this column here is going to be a ground. So every time you need a ground, you just take it from here. So for example, if you want to connect the ground here anywhere here in the circuit, just take it from here. Okay. One more thing related to the ground, guys, as I told you before, for example, if you have here a function generator, you are going to generate input this way. The other one has to go to ground. Okay. All the circuit should have the same ground. Same thing here. If you are using a scope, in the scope here, I want to measure what is the output. I'm going to connect this one here, and this one has to go to the ground. Be careful about this part. All the circuit should have the same ground. Okay. So what I told you here, it's a very good habit just to make one. So here, what you can do here, I can make this column, like for example, this one is a ground. I'm gonna make this one like positive 10 and or 15, whatever it is, and then I'm gonna make this one like negative 10. Okay. And usually, I think I give you here, you need to read this lab. Usually we use like colors. to differentiate between them. I think what I wrote here, let me see. Yeah. So here, usually we use black, we use black color for ground. Usually we use red for positive, and usually we use the yellow for negative. This is just a convention, okay? So if you miss it, for example, and maybe you are gonna make a wrong connection. So anyway, this is just a convention. Usually we do that, okay? One more thing, for this lab, we're gonna connect the bias this way. But in general, as I told you also in the lecture, here in this connection, we're using two power supplies, as you see here, to create, for example, positive 10 and negative 10. Usually we do that when you have a sine wave this way, and the sine wave has a positive side and negative side, okay? And also, sometimes we connect it using only one supply. So as you see here, we are not going to do this one in this lab, but I'm just teaching you. Sometimes we do it this way. For example, if you make this one like 5 volt, this will be 5 volt. You see what I'm saying? And here is the ground. That means, as I told you in the lecture, this bias voltage should decide or determine the maximum output voltage. So if you make it this way, so actually the output voltage should be limited between 0 and VCC, or 5 volt. In this case, if you select positive 15 or negative 15, so the output has to be limited between these two. Otherwise, it's going to be saturated, okay? Anyway, let's see if I'm missing anything else here. Yeah, go back here. Yeah, that's what I told you guys. They can be, you can easily, if the power connection are not correct, or even I told it happened to me by myself when I was a student long time ago. What I did, yes, I made correct connection, but I did not pay attention to the power supply. The power supply was, I think, 40 and negative 40, or it was really huge value. Okay, when I applied it, it made a crack, or I damaged it. So what you can do here, you need to make sure, do things. Connection should be correct, and values also should be correct. Okay. And I recommend once you finish it, before you connect, you can ask the TA to come and take a look. Okay. One more thing here, I told you guys, even I explained in the lecture, usually we can add a capacitor this way. Okay, here. So so how you, because this is okay. So here, yeah. So here you can connect a capacitor this way. Also, you can connect a capacitor this way. Okay, the part that confuses students, guys, when I say this is a ground, this is a ground, this is a ground, what it means? It means all of them are 1 point, but I don't want to complicate the figure and make it messy. So what I'm doing right now, so here all the circuits should have only one ground. So when I say this is a ground, this is a ground, that ground, it means they are connected together, but I don't want to connect them together just to avoid making the figure messy. Same thing here. When I say this is a ground, this is a ground, that means they are connected. They actually connected to the same ground. We always have one ground. But again, we make it this way just to make the figure simple. Okay. So, as I told you in the lecture, guys, we are going to have two capacitors. We are going to connect them this way. And this is the purpose of this capacitor, as I told you here. For any capacitor, any DC value here, DC voltage is gonna be like open circuit. However, for AC is gonna be like a resistance. We call it impedance. Okay. So actually here, as I told you in the lecture, we are going to use this one to stabilize the DC voltage. So here, actually here, if the DC voltage is this way, I don't need the capacitor. In reality, it's not like this one. In reality, DC, but we have some AC here. So if I do that, the AC will see this one like a short circuit. So I'm gonna get rid of this one, and then I'm gonna have here very stable DC value. Okay. So we're going to connect the two capacitors this way for the positive and the negative. We call it bypass capacitors. Here I explain exactly why we need it. So here I'm explaining what is capacitor. I already explained capacitor. And as from my explanation in the lectures as well, we have two types of capacitor. One, we call it ceramic capacitor, and that's how it looks like. and the other ones, this is how they look like. We call them electrolytic capacitor. Is that okay? For this lab, we are going to use a ceramic one. We are not going to use this. We are going to use this one in other labs, okay? But for this lab, we're going to use the ceramic one. As I told you in the lecture as well, for the ceramic one, they don't have a polarity, okay? So you can connect either way. There is no polarity, but this one is very serious. There is a polarity. You can see here, guys, look, there is negative here. That means this terminal it has to be negative and this terminal has to be positive. As I told you, if you make a wrong connection here, this one is gonna explode. So you have to be careful. Anyway, we're not gonna use this one in this lab, but we're gonna use it in the future labs. Okay, now how I can read the capacitance of the capacitor for the electrolytic, it's easy. Look, it's written here. 4,700 microfarad. Same thing, it's always written here. Okay, so it should be easy. However, for this one, it's giving you a code like this one. So now, how I can use this code to read the value? Very easy. Look here. If the code, for example, 154, okay, very simple. All what you have to do, the first two digits, for example, 15 multiplied by 10 to the power of the third digit, and the result in picofarad. You see what I'm saying? For example, if you see this one here, so this one is actually 10 to the power 10 to the first two digit is 10, so it should be 10 or 10 to the power of 4 picofarad. That's it. You see what I'm saying? Remember, pico, as I'm saying here, 10 to the negative 12. Nano, 10 to the negative 9. Micro, 10 to the power of negative 6. So this one here should be 10 to the power 10 to the power 3 picofarad, right? Anyway, so, and also look here. So for example, here, this one was 154, so it should be 15 times 10 to the power of 4 picofarad, okay? I can write it this way, right? Why? Because actually pico is 10 to the power of negative 12, okay? So if I take, if I just, and nano 10 to the power of negative 9. So if I divide this one, it's like, look here, because I know some students, these small things can confuse them. So this one actually 10 to the power of 12. It's the same thing, 10 to the power of 3 times 10 to the power of negative 9. 10 to the power of negative 9, this is nano, right? And then I'm going to divide this one by this value, which is 1000, right? Anyway, so here also, I list all the capacitor you have, okay, in your kit. So you can see here you have, these are, again, we're going to use a ceramic in this one here. So these are the codes you have for ceramic, okay. I think here I didn't give you exactly value, but I give you a range. So here, for this capacitor, I give you a range, but you will see right now, it's written here somewhere. I think it's going to be written in the experiment, okay? So, okay. So one more thing I want to just here remind you is that for the frequency response, I explained it in the lecture, guys. So here, any op-amp, there should be like a maximum frequency you can use. If you increase the frequency of the signal, if you make f is very large value, what's going to happen, because it has a slow rate, a limited slow rate, you will see the output is distorted. You see the output signal is not, so you will see at some frequencies, yeah, I have a very nice signal. As you increase the frequency, you will see like something started to be like noisy or something like distorted, okay? So this is something, one thing I'm going to ask you to do. So first, you are going to connect for at a good frequency. You will see how the output is very nice. Relation between input and output is as expected. It is inverting amplifier or non-inverting amplifier. Now I will ask you, just coming anyway. I will ask you, please increase the frequency until what happens? Either the signal is distorted because of the slow rate, or actually the gain is going to be smaller than the gain I have. Okay, for example, if the gain is 10 at a small frequencies, when I increase, it may happen that the gain start to go down, because this is another thing I told you here, guys. As for example, if the gain is 20, so you can work with frequencies here until 10 to the power of 5. If you increase it more than that, if you go beyond it, okay, beyond the 20, so actually the gain will be smaller than 20. So this is how you can measure the maximum usable frequency. All what you have to do, gradually increase the frequency, okay, until one of two things happens. Either the signal is distorted because of the slow rate, or the gain it's going to be less than the gain you have. Okay. So as you see here in this figure, guys, so here, if the gain is 20, so it should be when you change the frequency from 0 until t to the power of 5, it is actually, it should be something straight line this way, right? It should be this way, straight line this way. However, if you go beyond this value, the gain start to be reduced. Maybe slow rate is going to happen before that. But anyway, again, let me see here. Okay. So the first circuit you are gonna connect is this circuit. I know some student guys confused when you sometimes I make it negative here, positive here, or you can flip it. It's not. It's the same thing. Okay. So this is actually, you can see here I made a feedback from the output to the negative, and you see R1 is connected to ground, and you see the input is here. Okay. From what I explained in the lecture, this is actually the connecting off. This one should be non-inverting non-inverting amplifier. Okay. And actually the gain, which is V output divided by gain, this is what I'm expecting. That's what I want you to see here in this lab. 1 plus R2 divided by R1. R2 is the feedback. Feedback means, guys, the word feedback means you get from the input and you connect it to the from the output to the input. So here R2 divided by R1. This is the gain I am expecting. One more thing, guys, this one should be non-inverting, which means, as I said in the lecture, that's what you have to see. If you apply a small signal like this one, you should see the other signal amplified by this amount, by this value, and it should be in phase. In phase means this is a positive, this is a positive. This is a negative, this is a negative, okay? Because in case, and this should be the second case, in case of inverting amplifier, if you have signal like this one, you will see the other signal is going to be, yes, it is amplified, but you flip it because the gain should be negative R2 divided by R1. Okay, you will see that in the second experiment. When input is positive, output is negative. This is something you need to look for, watch here. Okay. Anyway, so here I give you a so for capacitors, for these two capacitor, I told you can use any value in the range of 10 nanofarad to 100 nanofarad. Okay. For the resistors, I give you these values here. 18 for the feedback resistor and 2.2. That means the gain should be 1 plus 18 divided by 2.2. So whatever value you get, okay, should be, I think the value should be somehow very close to 10, something like that. Because 18 divided by 2, it is 9. Okay, maybe somehow close to 10. Anyway, you need to see. So this also, you need to verify. Okay, you need to calculate this gain and verify it. How can I verify it, Keyman? I will tell you how can you verify it, because actually the output here, okay, let me not calculate it, but let me give the exact value. Let me use the calculator. Okay, so here it is actually 18. Okay, 18 divided by 2.2. I'm gonna add 1. Yeah, so it's actually, so V output should equal to 1 plus RF or R2 divided by R1 times the V input. So when I did the calculation, it was 9.18 V input. So the input has to be multiplied by this value, okay? Which means if I input here and input here, guys, for example, here 1 volt and here 1 volt, so here's actually positive 1 and negative 1. How the output should looks like? So yeah, you are gonna multiply the peak here and this one by this value. So what I have to see here, this one here, 9.8, 18, okay? So you multiply the input, the peak value here, same thing here should be negative 1.8, okay? Same thing for any other input value, you should get the same relation until what? Until it is saturated. Yes. When it is saturated, that means the output is not going to be pure sinusoidal again. The output will be clipped. So that's also one thing you need to see. It should be clipped here. And the value here, because it cannot produce voltage that is greater than the bias voltage. Okay. So I give you here R1, I give you R2, I give you the value of the capacitor. For the bias voltage, again, who's gonna tell you how much bias voltage I can put here? Very simple. You need to go to the data sheet. The data sheet should tell you, okay. But from the data sheet, it tells you it's written, it's recommended to be positive and negative 15, but you can use anything between positive and negative 10 until positive or negative 22. So, okay. This, and in case if you are using only single supply, so actually it can go for single supply means one is zero, one is ground, and the other, we're not going to do it here, but just to understand the topic. Anyway, so here and the other one maximum should be 44. So I recommend, it's up to you, okay? But you must be in this range because that's what they are telling us. But just I'm as long as you can make it like positive and negative 50, okay? So you need to make sure before, this is a mistake I made as a student, okay? Before you connect the power supply, make sure it's the two power supplies are 50. I remember the mistake I made. I didn't pay attention to the power supply. It was 40, I guess, 40 and negative 40. So it correct right away, okay? So, because it's too much. But anyway. So that means, guys, the output voltage I can get should be between positive 15 and negative. You cannot. So as the output here is something between positive 15 and negative 15, you will see a very nice sinusoidal. Okay. However, if you increase it too much, it's going to be clipped because simply I can't give you more than. So it's going to be clipped here because it want to go more than that. It want to go, but I can't. Right. For sure, for amplifiers, that's a bad thing. If you want to use amplifiers, we consider something like this, it is distorted. You distorted the signal. So we try to avoid the situation. It's not something good, right? It's a bad thing. Anyway, so I'm saying it here, guys, and I said in the lecture many times. All the devices you are using, we have only one ground. Okay, so the circuit, so the ground of the circuit, the ground of the function generator, the ground of the scope, the ground of the power supplies, all grounds have to be connected together. Otherwise, the circuit is not gonna work. Okay. Anyway, so here, as I told you here, you have to use two channels because until now we need two power supplies, right? So here, yes, we need two power supplies for the bias voltage. So now you need to use two channels. Make sure the two channels are, if you decide to select 15, make sure the two channels are 15. Okay. Let me see here. Okay, so now we're gonna do what we're gonna do. We're gonna do only two experiments, guys. The first experiment, which actually this one here, again, I don't see this lab difficult. The only difficulty here because we are gonna use here in this one here, I'm gonna use two power supplies here, two power supplies, and then here you need to connect sinusoidal, so you need to use a function generator here. The function generator should have we're going to use only one channel from the function generator. One channel come here. This one has to go to ground, right? At the output here, because I want to see, I want to visualize the input and the output. So here, for the scope, okay, I'm gonna connect one channel here. For sure, the other channel has to go to ground to just visualize the output. Not only that, I need to use another channel from the same scope. I want to use another channel to connect it to the input as well, because I want to see on the scope, if this is the input and this is the output. You see what I'm saying? So I want to display two signals on the scope. Again, it's not difficult. It should be easy. The only difficult, because even here, look at the connection here. You just connect here R1 and R2. Just you connect it between pin number 6, pin number 2, from pin number 2 to the ground. The only difficulty, because just we are going to use multiple channels. Okay. So number one, you need to connect this circuit as I told this way. You need to connect the circuit this way. Okay. You have a function generator, and here you have we are going to use two channels of the scope so that I want to display both input and out. Okay. Anyway, let's see what I'm asking you to do right now. By the way, if you still you don't know, I can tell you here the oscilloscopes we have. You can actually use a USB memory to store pictures, images. Is that okay? So either because one in the final report you need to put the picture. So for sure you can, just in case, you can use the you can take a picture using your phone, smartphone, or you can also, if you have, you can bring a USB so that you can download a picture from the oscilloscope. However, you need to check, make sure, because you maybe are going to put USB and then you ask the oscilloscope to put a picture and then it doesn't work. Just make sure, or you can do both just in case. So you can store the picture using USB, okay, memory. Also take a picture using so that, or you can check if it is stored or not. Okay, anyway. So for this experiment, guys, we are going to do two things. Case number one, case 1.1 and 1.2. Look let's see what I told you. What I told you, for the input, you need to select the sine wave. You need to make the frequency is 800 hertz. Okay. You need to make sure peak to peak is 1.2. Okay. Peak to peak. That means the input signal here has to be 0.6 and negative 0.6, because peak to peak 1.2, right? And make sure you don't have a DC offset. DC, if you have a zero DC offset, that's how it looks like. If you have a DC offset, it's going to be shifted up this way. Make sure you don't have any DC offset. Okay. Then, so this is the first thing. And then if this is the input, okay, I want to see what is the output. That's it. So the output again has to be something like that. I want you to take a picture for both of them. I just want to see, I want you to see the amplification. Did we do amplification or not? Amplification means I'm going to multiply this one by a value. I think what value we calculated? It was 9 point or 8 point. I don't remember, but yeah, it was 9.18. So I want to see here this voltage should be multiplied by this value. Okay, so that we did amplification. The second part here, look here, the second part, find the maximum useful frequency for the circuit by increasing the signal frequency. So I'm telling you here, don't change the voltage, keep the voltage same, but actually gradually, okay, you have to increase this frequency. Okay, so you will see, guys. For example, when the frequency is 1 kHz, the output is 1 kHz. Both of them are sine waves. Both of them are nice. Everything is perfect. You increase it 2K. This one is 2K. 3K. So it should be this way. Okay. However, at a certain point, and this is what we call maximum usable frequency. At a certain point, because as I told you in the lecture, when you increase the input frequency, you're actually asking the device. You are asking the device to respond fast. So when you change as you increase the frequency, you actually change the frequency fast. So the question is that, can the device keep track? It can change fast. Okay. The answer is yes, until a certain frequency. So you have to increase the frequency, okay, until one of two things happen. One of two things happens, as I told you. Number one, the signal starts to be distorted. It looks like more, it's not a pure sine wave anymore, right? Any kind of distortion you should see. Number two, the gain actually, the gain should be 9.18, right? So, or maybe the gain is gonna be reduced before the slow rate has an impact. Okay, whatever any one of them. If you see the gain is not 9.18 anymore, okay, or there is a significant reduction or some reduction here, so that means this is a maximum frequency, or distortion have. I think in the past we used to have distortion first, but again, if you have a chip that distortion didn't, or the gain, even the gain is reduced, that is not that's not the usable frequency, because I want to use a frequency that gives me the same gain, this gain, right? The same gain all the time, So if this happens, so just tell me, okay, I tested different frequencies until, for example, some value, whatever the value, if I don't know, because even this value is different from maybe it's different from one chip to another. So don't ask your your neighbor, your neighbor station what value you got, because maybe this value different from one chip to other because it's related to manufacture and other things. Okay. So the second part here is actually I want you to see distortion. The second part here, yeah, I want you to return again to 800 hertz, 800 hertz, which was the original case here. Now, this time, I'm asking you to increase the voltage. Look here, increase the voltage to 10, right? I'm 100%, when the input is 10, 100% distortion is going to happen. Why? Because if the 100 is 10 and the gain 9.18, I guess, yeah, 18, that means the output has to be 91.8, which for sure it's much bigger than both a negative 15, which is the bias voltage. So in this case, you can even make it like even smaller than 10. You can, again, I'm not asking to do that, but for learning, you can do that. You can just increase see, this time, keeps the same frequency, but it changes the voltage gradually and see what's happening, right? You will see, as long as you are not hitting, as long as you don't hit the limits, which actually is the bias voltage. For example, if I decide to make the bias voltage positive 15 and negative 15, as long as, for example, if this is the output, yeah, it's very nice. If you increase it a little bit, yeah, it is very nice, because when you increase the output will increase until, if you want to use amplifier, so you just touch. So this should be, this is your limit. However, more than that, you are gonna get a distorted signal. So it's not sine wave anymore. You will see something distorted this way. Okay? This is for the first part. For the second part, guys, you are not going to make a major change in the circuit. Okay, it's very important to try to connect even the circuit before coming to the lab. You are not going to make a major change in the circuit, because look what you have to do here. Or let me see here. So here, what you have to change, everything is the same. However, here pin 3 was connected to input. Look here. This pin here, let me come back here. Yeah, because this time I want to use inverting amplifier. So all what you have to do here, guys, is that this pin will be connected to ground, right? And this one will be input. The input is going to be from here. You see what I'm saying? And this resistor, I'm going to change it to another value. You will see right now. Not only that, as you see. So what I want to tell you here, don't dismantle the whole circuit. No, it's just a minor change it here. But for everything, almost bias, everything will be the same. Okay. So what I'm saying, yeah, this is how you have to connect it, right? So please don't be confused. What I did here in the previous one, I made a negative here, I made a positive here. This time I'm making negative here. But don't be confused. It's the same thing, guys. This is same to the other one, but for I don't know why, but sometimes I make this way, sometimes so even you see this feedback always from output to negative. So when the negative was here in the previous figure, it was here. So don't be confused in these very small things. Okay. Anyway, so here in this one here, you have to this configuration. This configuration, if I just, listen to me, if I just remove this branch here, this is inverting amplifier. If I add it, it becomes a summer or adding circuit. Do you remember when I told you, if you want to make adding circuit, it's the same thing. This is, if I just remove one branch here, this is the configuration for inverting amplifier. If I add this, another input, it becomes a summer or adding circuit. Okay? So here I give you the value for resistors. Okay? Value for the resistor. Capacitor are the same, bias are the same, connection with the scopes also will almost be the same. Anyway, so here, as you know from this configuration, as I told you in the lecture, the output should equal to negative R5, which is this one, divided by R3. The input 1 plus R5 divided by R4 times the input 2, right? Just I want to make sure what you are going to get is similar. That's what I thought I did in the lecture. Maybe I'm wrong, right? Maybe I'm teaching something wrong. That's why you are doing experiment to check if it is true or not. You see what I'm saying? So this is just the first part here, in the first part here. So now This also different from the previous one. Now, guys, I need two channels from the function generator. So here, if you have a function generator here, for the first channel has to be here. And again, for this channel, the ground of this channel is going to be connected to the whole ground. Everything has the same ground. Same thing here. I'm going to use a second channel for this input, right? And then the ground of this channel also will go to ground, right? So anyway, so here I'm going to use two channels for the function generator. Let me see what I told you. Set the function generator output one, channel one, to create a sine wave with frequency 700, and this is the big to big value 2 volt. So the first one is actually sine wave. Okay. For the second channel or second output, I'm asking you here to create a square wave with this frequency and actually with 2 volt with 2 volt amplitude. Okay. Which is actually 1 and 1. Make sure again, it's going to be something like that. Yeah, 1 and -1, this one. Okay. So as you see here, guys, I'm adding, listen to me, I am adding sine wave. I'm adding sine wave. So here one signal is actually a sine wave with 700 hertz. This, for example, here. Okay. The second one is a smaller here. For example, you are adding here for just something like that. Okay. So that means, and as I told you in the lecture, guys, if you have a sine wave this way and then you add like a DC this way, you are going to shift it up. But if I added something negative, you are going to shift it down. So interestingly, what you are going to see, you're going to see this part. After you add this part to this voltage, you will see this part shifted up. And then you need to see this part when you add it to a negative, it should be shifted down, right? So it's so what you have to see, something like, yeah, this is here, and then it has to be, so that's what, anyway. So that's what I'm expecting. It may be wrong. Let's see. Okay. Or this is our understanding. You do the experiment and see how it looks like. Okay. This is for the first part. Okay. Maybe, yeah, I think, I'm sorry. Yeah, it's what I did is true, but because there is a negative in the relation, so actually here the output will be, yeah, so here is if the input is this way, so actually the output, because there is a negative, will be this way, right? Same thing if the input is actually square wave this way, the output should be inverted this way because there is a negative. So everything I explained is true, but actually just consider it will be inverted. Okay. Anyway, so this is the first part. First part, actually, you are verifying the summation. You want to see if indeed the circuit can do addition, because that's what of the application I explained. The circuit, you can add two signals. Okay, you will see how it works or not. Okay. The other thing here is for the second part is very easy. Second part, actually, what you have to do here, I want to look here. If one input here, you make it a ground, you actually canceled it because this is a ground, this is 0 voltage. This is here 0 voltage, so 0 volt. So if I make the input here ground, so you actually almost cancel it. In other words, you're adding V1 to 0. So if I do that, actually, it's almost the same thing like you remove to this one part here, and now the circuit becomes like inverting amplifier. Okay, so now it's going to act like inverting amplifier. You will see when you have like an input this way, you will see the output will be this way. Okay, so you need to see, that's what I taught in the lecture. Is that true or false? This is the relation R5 divided by R3 times V input 1. See if this is true or not. Is that true what I explained here? When this one is positive, this one should be negative because you have a negative here. That's what you have to do in the second part. So in the second part, I'm asking you to use only function gen to generate one sinusoidal, right? Yeah. And then for the second one, I'm asking you to connect it to ground. I think that's it. So again, I want you to just pay attention because what happened in the past, I don't know, maybe because this one, again, this lab, I don't, what happened, the best student somehow struggled in this lab. I don't see it a difficult lab, but all what I see is you have to use many things, all right? You have to use maybe one or two channel for function generator, For the scope, you may use multiple channels for the oscilloscope. Also, you are going to use power supply as well, right? And maybe this is the first time for some students to use a chip. That's it. But hopefully I made it easy in this video here. So here we have a pre-lab. In the pre-lab, you have to read this part here. Let me see if there is anything I need to clarify. Yeah. Just here, I'm telling you, you need to connect it before coming. I give you 6 points for that. I want you to find the relations in the 4 cases, what you are expecting, what is the theoretical values, okay? One more thing here, just you can also do simulation. I give you even a video here to explain how can you simulate an operational amplifier, okay? You need just watch the video, do similar to the video to learn how can you use LT Spice to simulate operational amplifier. Again, should be easy, very easy. Here, this is for the data you have to collect here, guys. You need to tell me what supply you use. I recommend, as long as in the data sheet it's saying positive 15 and negative 15, okay, you can just use this one, right? Here, I'm asking you, give me the picture of the first 2 cases. Are this picture similar to what are you expecting or not? And then, from the picture, find the relation, okay? What do you mean? What I mean, look here, guys. If you have a signal, something like that, and then I have another signal like this one. If I tell you this is the input, this is the output, can you calculate the gain? Can you calculate the gain? Yeah, for sure. I'm going to see what is the voltage here, A. What is the voltage here is B. You can take it either only peak. So the gain should be B divided by A. Or you can take it peak to peak, whatever value you have here, but here you also have to take peak to peak. So if I divide the output voltage by the input voltage, this gives you by this way you can measure the gain, and then you need to compare to it to the gain you calculated or you are expecting. For sure, maybe it's a little bit different. Why? Because as we said before, you have resistors, right? You are assuming the resistor you are using, for example, if you have 1 k ohm resistor, and the resistors are very important here because the gain is actually a ratio of resistors, right? So as we said before, when it is 1 k ohm, actually it may not be exactly 1 k ohm because of the tolerance. Okay, so it's okay. It's not a mistake if you can. But for sure, we're not expecting like if you are expecting gain of 9 and then you are going to get gain of 3. No, this is wrong, right? But if you are expecting 9 and you get something like 8.8, 8.9, something too close, yeah, this is something I can justify. I can say my calculations were based on either resistors. Resistor may be different, okay? One more thing you need to do here in this lab, I forgot to tell you guys, because resistors are playing a very important role here, guys. So what happens is that some student pick up wrong values for resistors. What you can do, as I told you before, when you go to the lab, it's gonna take just maybe less than 1 minute. Just use the ohmmeter and make sure your resistors are correct. That's it. Because what happens is if you put a wrong resistor, results are not are wrong, and we don't know the reason. You will check everything. Let's check this one. Let's check this one. Let's check this one. Okay. So just to try to avoid mistakes, yeah, once you go, just use the ohmmeter. Make sure the values of the resistors are correct before using them. Okay. The other thing here for the maximum usable frequency, just give me a picture. Show me. You tell me. I increase, for example, at a certain number, whatever this number is. For example, at 40 hertz, I decided this is the maximum because at this value, the signal became distorted, and this is how it looks like. Okay. Same thing here. I'm asking here about the distortion, about the saturation. What happens here when the voltage is too large? Okay, for sure, because so very important thing, guys, to learn. So that means everything has a limit, right? So the operational amplifier, the output voltage has a limit. Frequency I can use also has a limit, right? And this is something you need to learn here. So here in number 4, you can tell what is the limit for the input frequency. What is the limit for the voltage? Because guys, the way when you are using amplifier, the output frequency has to be equal to input frequency. This is always the case. I don't change the frequency. It has to be the same frequency. If here I input 1 kHz, I'm expecting to get 1 kHz here, right? So anyway, the signal should not be distorted anyway. So same thing for the summing amplifier. Also, I'm asking you to give me the pictures. Are these similar to what you are expecting or not? And then again, I will ask you to determine. Look here, experimentally, you are determining the relation between output and input, and then check it or compare it to the calculated and the simulated values. Okay, I think that's enough, and good luck, and thanks so much.